In this video, you will learn how to create a dynamic and random arrangement of triangular facade panels. We'll start by building a flat triangle facade. Then I will show you how to properly align the corner normal vectors of the mesh. Next, we'll sort all of the mesh vertices based on their x, y, and z coordinates simultaneously. This will allow us to create geometry that represents the facade substructure. By following these steps, we will be able to create a versatile and visually striking facade design. Let's get started. First, we'll create a point using point container. Right-click, set one point, and find a point in Rhino. We'll use it as origin of XY plane, connect with a point. We can rotate this plane using the same component, connect with the plane, and in the A input we can define angle. So we'll create slider from 0 to 360, connect with A, and don't forget to set degrees. Once we set the rotate plane, I'm going to turn this off, and this guy I will use it as a base plane of the rectangle. In X and Y input, define dimension of the rectangle. I will create a slider, let's say 42 for the X and 20 for the Y dimension. But if we take a look here, we need to connect domain. We can place a slider, but the center of the rectangle can connect, but this point here will not be placed in the center of the rectangle. So if we want to use this plane as a center, we need to construct domain, and the start and end of the domain should be in total 42. So if this is 42, we need to create a domain from -21 to 21. First, I'm going to divide this value. Once we get 21, I'm going to take the negative value, place in the start, and 21 will be placed in the end of this domain. And this is how we created a domain from -21 to 21, and I will place it in the X value. The same logic I will apply for the Y dimension. So we'll copy this one, and I will select here 20 and connect with the Y. Here, if I rotate the plane, the rectangle is rotating as well. In the next step, I'm going to extrude this rectangle along Z direction, find extrude component, and in the D input, extrusion direction, I will use unit Z, connect with D, and now we need to define the amplitude of the vector, or for how much we want to extrude this rectangle. Once again, I will create a slider, and let's set 11. Once we get single open B-wrap, I'm going to deconstruct this B-wrap in order to get 4 surfaces. So we'll type B-wrap deconstruct, connect with the extrusion, and in the F output we have 4 untrimmed surfaces. These 4 surfaces will subdivide using Lunchbox plugin, and from here I will take component triangular panels A. So this one. I will connect with the surface, and you can see here how we created the subdivision. Now we need to define how many divisions we want to have along U and along V direction. So we have 2 directions of each surface, so U and V. And we need to define how many divisions we'll have. Let's create slider 15 for the U, and I want to get this kind of result. So if we have, let's say, 15 divisions, I want to get a panel which will have another, or this horizontal dimension, 3 times larger than vertical dimension of the panel. So if this is X, horizontal dimensions should be 3 times X. Here we don't have a square, so we cannot divide this by 3. Actually, we need to have 3 times less divisions because these dimensions should be larger. So first, we need to find the dimensions U and V of each surface, dimension along U and along V. One dimension is the same, the vertical one, but the horizontal one, it's not the same. We need to find the ratio between V and U. So I will type division, divide U with V, and here we get the ratio. And this ratio should be multiplied with 15. We'll get the panels that are almost like a square. But if you remember, I want to get the panels that has this kind of dimensions. So this horizontal one should be 3 times larger. This guy, or these values, should be divided by 3. And now we'll get the result that we want. If you want to get horizontal dimension, which is 4 times larger than vertical one, we can type here 4. Or we can type 2 if the horizontal dimension will be twice the size of the vertical one. I will place it back 3. Once we get panels, I want to convert them into mesh. So I will type here simple mesh and connect with the panels. Now each surface or each panel is converted into single mesh. Now I want to flatten the list of meshes, join them and weld. I will use component weaverbirds join meshes and weld from the weaverbird plugin. And in the W input or the input, I will set boolean value true because I want to weld the mesh. As a result, we get a single mesh. In the next step, I want to take each vertex of the mesh and I want to move them along their normal direction of the mesh. So in order to extract vertices and their normals, I will take component deconstruct mesh, connect with the mesh, and here we get vertices and here we get the normals. If I want to visualize these vectors, I will type vector display. Anchor points will be vertices and the vector will be normals. If I zoom in here, we have a problem with corner normals. So all the normals that are placed in the corner of this geometry. Here, the vertical ones that are not placed in the corner are fine. But if we zoom in here, the bottom and top one are not the same as the rest of the normals. I want to modify them in order to orient them in the same direction. We need somehow to take these normals and place them in the same branch, find the average and place it back to each normal. I want to take each vertex, I will deconstruct the vertex, and I will check are the X and Y components the same as the corner points or corner X and Y coordinates of the rectangle. So I will type discontinuity in order to extract corner points of the initial rectangle. Take these guys, deconstruct, and I will check if the X coordinates from this list are the same with the X coordinates from this list. If we take a look, here we have 4 items and here we have almost 900 items. So I need to graft one of these lists in order to test each point of the mesh with these 4 X coordinates. Before we test are these two values equal, I need to round them. So I will use expression. First, I'm going to remove Y input, and in the expression I will type round X, 3. So which means each of these values I will round to 3 decimal numbers. And the same logic I will apply to each of these outputs. Now we can test are the X coordinates of the mesh vertices are the same with the X coordinates of the corners of the rectangle. So we get first here true and false values, and here we get another. If both of these two conditions are true, we'll create a new pattern and we'll extract these normals. First I will type gate and test if these two conditions are true. Once we get the pattern, I will take a look at the data tree, and we have 896 branches, in each branch 4 items, and here we have a single branch with 896 branches. So we need to flip the matrix in order to get 4 branches, in each branch 896 branches. Or if you want to get this data structure without flip matrix, you need to graft these inputs, and I will ungraft these guys and we'll get the data tree that we need. I will use call pattern because we have matching data tree or matching number of items or list length, and I will connect with the normals. And here we get 4 branches, in each branch 16 items, which means we have these 4 normals in the same branch. I will use the same logic for the vertices. So here we get the vertices and here we get the normals. If I take vector display, connect here, turn this on, and we extract only these normals. So these 16 normals are placed in the same branch. Now, if I take these normals and find average, we get a single normal, and I will connect here. Now you can see that we have the normals in each corner that are the same. So this is what we need. Now we need somehow to replace these normals with the normals that we had here, and the rest we will keep the same. So the normals that are not placed in the corners. In the next step, let's take a look at this list. We have 4 branches, in each branch single normal. Now I need to duplicate normals from each branch as many times as we have items here, because we have 196 items. I will take list length, connect with this one, and I will repeat these normals 896 times. Now we get 4 branches, in each branch the same number of items as we have here. Now I will try to find in which position these normals are placed in the original list. I want to keep only index items where the corner normals are placed in the original list. So for that, I will use sift pattern. This is the list that will be placed in the sift, and the pattern will be the one from here. Now I will take the output from I input, and here we can see that normals that are placed, let's say, in this corner are positioned at the indices 18, 19, 29, 39, 49, and so on. But we have here 4 branches. In the original list of normals, we have single branch. So in order to get single branch with the same number of items, I will flip the matrix and we'll get 896 branches. In each branch 4 items. As we don't need index of each normal, we just need to know in which branch the normal is positioned. Now I will use clean tree. Once we clean tree, in the result we get the normals that are placed in 896 branches. Let's say this guy is placed at the index 535 in the original list. In order to replace these new normals with the normals that we have here, I will graph them and we'll get the same data structure as we have here. If we compare them, we get 896 branches. Inside each branch single item, and here we have the same. In order to replace them, I will use component combine data, and these new normals I place in the 0. The original normals I place in the 1, which means we have in the branch 0 this normal and this normal, but this one is placed in the 0 output, which has priority. This will be placed in the final out. The same logic for the branch 1. So in branch 1 we have this normal and this one, but because this one has priority, because it's placed in the 0 input, this one will be placed in the final output. But for the branch 2, we don't have any value, but here we have one. So this one will be placed in the final output. Basically, it means all these normals will be replaced with the normals in that branch from the original list, and in the result, final result, we'll get new normals. I will flatten the list, and once again I will take this vector display, connect with the new normals, and you can see that the normals that are placed in the corners are the same. Once we get the normals and the vertices, we can use component move, so we can move these vertices along normals. Once we get the vectors, amplitude can be generated from the random component. So we'll create 896 random values. So first let's take the list length in order to set how many random values we'll create. And in the R input we should set domain. Basically it creates a domain of random numeric range. And the start domain can be, let's say, 0.2. End of domain will be 1.4, which means the minimum number in the random output will be 0.2, the maximum value will be 1.4, and within this domain we'll generate 896 random values. Here we can set seed random engine. If you change this slider, you will get different randomized values. And I will place in the amplitude, place in the T input, and once we move them, we can see that these points are moved inside. But if I want to move them outside, I can reverse these vectors. Once we move these points, we need to construct a new mesh. So I will type construct mesh. This will be vertices, and we only need faces of mesh object. faces will be taken from face output. And this is how we created a new mesh. So if I change the slider, we can generate the maximum value of random amplitude. Here we can set different randomized values. And if you want to convert this into surfaces, I will type face boundary, this one, extract polyline curve, and we can create a surface using boundary surfaces. In the next step, I will try to create geometry that will represent substructure of the facade. Basically, I need to take these vertices that are placed in this line, also these vertices, and I want to take all of them and place in a single branch. Let's say in the branch 0, this will be placed in the branch 1, this will be placed in the branch 2, and so on. How we can extract these vertices and create a branch structure like this. I will go back to our initial mesh. I will turn this off, and I will take these points that are placed in the same vertical line and placed in the same branch. So let's first take these points, and I'm going to deconstruct these points, and I will sort them based on their x coordinate. Let's type sort, sorting value, and here we get points based on their x coordinate, and here we get x coordinates. Now I want to divide this list of points based on their x coordinates. Points that have the same x coordinate will be placed in the same branch. So I will type here delete consecutive, and here we get different x coordinates of the points. And I'm going to use member index. And these members I will search for, and set to operate will be this one. We need to take an output, which is a number of occurrences of the member. Basically, how many times this value is repeated in the list. So this one is repeated 16 times, then this one 16 times, and so on. But it will be different if we rotate to 0. Let's have a look. The first one is repeated 160 times. Why? Because all these values here are placed in the same x coordinate, and these guys as well. So here we have 160, here we have 160, then these two are placed in the same coordinate, so this is why we have 32. And now I will use partition list to divide this sorted list of numbers, and I will use an output as a size of partition. As a result, in the first branch we have 160 items. Let me visualize this. So if I take points from the 0 branch, we have these guys in the branch 1, and so on. Okay, now points from the same branch we need to sort based on their y coordinates, which means these guys should be placed in the same list, this one in the same list, and so on. All right, I will use the same logic as I use here. First, actually, I need to deconstruct them, and I need to sort them based on their y coordinate. Now I will take these y coordinates that we have here. Let's take a look. And I will use delete consecutive, this one. Here we get the list of different y values. And once again, I will type member index. This should be placed in the member to search for. And this is the list to operate. Once again, I will use an output in order to divide this list with the partition components. So this will be the list to divide, and this is the size of partition. Now we have 56 branches, in each branch 16 items. Explode tree to visualize first 2 branches. Here we have the list of points in the branch 1, the branch 2, and so on. And in the last step we can deconstruct once again in order to sort the points in the same list based on their exact coordinate. And if I use point list, we have sorted points first based on their x, then based on their y coordinate, and lastly based on their z coordinate. Once we sort them, we can create a polyline. But how we can sort list of points that we have here, because they don't have the same x, y coordinate. What we can do, I will use index, item index, and I will try to search these items in original list of points or the list of vertices. As a result, we have items where these points are positioned in the original list. I will take these items and use it to reorganize on this list here. If I use polyline, we'll create the polylines that we need. Let me turn this on. All right. Now I will take these polylines and these polylines, and I will create the surface between these two. So we can create the surface using ruled surface. I can also create the lines. Here we have one list of points. Here we get another list of points. And we can split this list with the list of lines that we just created. So let's type surface split. And in each branch we'll get 15 surfaces. I will extract the outline of each surface, and we can offset it with the offset curve in the direction. Because I want to offset inside, I will take negative component, and here we can set offset distance. Once we have outline of original surfaces and the offset one, we can merge them. Don't forget to graft this guy in order to match data tree with offset curves. And inside each branch we should have 2 items. Once we get 2 items, we can create a loft surface. And this is how we created geometry that can represent the substructure of the facade. If we change seed number, you will see also how the substructure is modified as well. In the extended tutorial, you will learn how to generate unique and interesting design by creating random arrangements of triangular faces based on their distance from an attractor curve. You'll have the ability to adjust the range that determines which faces will be affected, allowing you to control the degree of randomness in the final design. The faces that are displaced from their original position will be perforated using populate and triangular mapping components, adding another layer of complexity and visual interest to the design. You can get the access to the extended tutorial on our Patreon page, and with that, you will get access to all of our other extended tutorials and project files. The link is in the description. If you'd like to know exactly how to create complex projects like these, and if you're interested in step-by-step learning approach starting from zero, make sure to check our Grasshopper complete course, where you'll find over 60 hours of video material structured in a form of video library, covering in depth more than 500 Grasshopper components through practical examples. And you'll have access to us personally, so we can answer all of your questions right away. The link is in the description.